Okay, let's go ahead and get started. Today, we're going to talk about a principle that is one of the most important principles in your everyday life. It's the principle that lights up our cities. When we flip the switch to turn on the lights, we're not connecting to a great big warehouse full of batteries. The current that lights up our cities is generated through a principle called magnetic induction. And that's what we're going to talk about today. And it's called Faraday's law because Michael Faraday was the first one to teach us about magnetic induction. So let's start today by let's start the day with a prayer. Who's feeling ready to pray today? Good, sir. Thank you.
Dear Heavenly Father, we are truly grateful for today. We're thankful so much for the opportunity we have to professor today and for the miracles we've been able to see in our lives. We pray at this time for thy spirit to reside in our minds and our hearts, that help us please understand these principles today, that we may be able to get any questions we have answered, that thy spirit will be able to teach us from on high. Love you, Father, we say this in the name of Jesus Christ. Amen. Amen.
Amen. Thank you. I just never get over the fact that we can do that and I don't get fired. I mean, it's so fun. I also can't get over the fact that in every lecture hall I go into, there are 2 half-eaten loaves of bread. That never happened in Montana. Okay, let's start by taking attendance here with our clickers. And just a second, I'll get us started. Okay, now you can click. Get your clicker out, Stephen. Quick, 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 quick. Okay. Have I got everyone? Okay, we're here. Good, good. So last day, we ran out of time before we could talk about the electric motor. And there are many, many different designs of electric motors, some more complicated than others, but they don't have to be complicated. I have made electric motors out of just wire that I've wrapped around in a circle and propped up on a couple of stands and used a magnet in my hand. The principle is fairly basic. Whenever I have current running in a loop, that current loop looks all the world like a bar magnet. And if that loop is free to rotate about an axis, it looks like a bar magnet that is free to rotate about an axis. And that's really a compass needle, right? And so if I had an external magnetic field, that's what these blue lines are, created by some bar magnet, horseshoe magnet, electromagnet, doesn't matter. If I had current running in this loop, it would become a compass needle and it would line up with the magnetic field. Now, that wouldn't be a very impressive motor. It would just go bonk, okay? But if when it gets here, I could reverse the direction of the current so that the compass needle pointed the other way. In other words, if I let it line up and then I change the direction, do you see that? It was coming out at the top and suddenly I change it so it's going in at the top. That forces the compass needle to change direction, and now it's not lined up anymore. Well, we know what it'll do. It'll try to line up. And as soon as it lines up, I have to change the direction of the current. I have to switch it, reverse it, so that the compass needle changes direction again. And it just keeps on lining up. That's all there is to a motor. Okay. Now the secret is, how do I get that current to switch directions at just the right time? At just the moment when the magnetic compass needle is lined up with the external field? Well, what we do that is, the way we do that is with bushings, okay? Sometimes it's called commutators, filthy commutators. So you see that one of these bushings is connected to the positive terminal of the battery, one to the negative terminal. And so every half turn, I'm going to get a different one of these leads. This one is connected to the negative terminal here, but as soon as it goes halfway around, it will be connected to the positive terminal. Now, this story will not help you on the exam, but I was visiting our daughter. She was living in Seattle at the time, and this thrift store had this enormous commercial generator that was super expensive, but they were selling it for dirt cheap because it didn't work, okay? It did not work. And so I bought it for like $100, and I took it home, and with about 25 cents worth of emery cloth, I went in and I cleaned off these leads that were completely coated over with some sort of deposit. And suddenly it was working like new. Physics can help you in your everyday life, people, okay? It's very simple. Now, I've got an example of an electric motor here, and the people in the cheap seats in the back aren't going to be able to see this very well, but what we have is a horseshoe magnet here that's setting up that magnetic field. That was the blue lines, And then we've got these coils. Those are the ones that we're going to turn into little compass needles. And the important thing, the commutators, are these things here. You see that there's a collar, a copper collar here, but it's really two half collars. It's slit right there. And so every half turn, I'm connecting this collar to a different side of the battery. And so that's how I switch the direction of the current. And the magnet just took my microphone. Okay. Let me demonstrate this. I'm going to put current through this thing. And let me slow that down. Speed it up. Can't hold it much longer, Captain. See if your neighbor could build an electric motor later this afternoon. Talk to your neighbor. Okay. We, last day, we had a demo that we called the jumping wire. And you remember what we did is we took a horseshoe magnet like this one here, and we used a battery to drive current through a wire such that the current was coming towards you. Now, because this is the north side of that horseshoe magnet and this is the south side, a magnetic field comes out of a north and into a south, the magnetic field is that way. We were sending current this way. And by right-hand rule number 1, I reach in the direction of the current, I wave in the direction of the B field, and the force is my thumb, and it jumped. And that was the principle that we just saw driving that motor right there, that force on a current carrying wire. Well, now we're going to do this a different way. What we're going to do instead is we're going to get rid of the battery, and you see that the battery is clear over on the other table. And instead, I'm just going to hook that wire to this galvanometer, and I'm going to let you see that galvanometer. There we go. Now, if you look at the right screen there, what I'm going to do is I'm going to take a wire and I'm going to move it down between the poles of that horseshoe magnet. Now, it will be helpful for today and Tuesday to think of wires in a very cartoonish way. Think of these as plastic tubes that contain a whole lot of positive charge carriers. And so when I push this wire down between the poles of this horseshoe magnet, I'm taking all of those positive charge carriers and pushing them down. I'm giving them a velocity that is down in a magnetic field that's to the right. Now, use your right-hand rule here. The velocity is down. I turn my wrist so I can wave my direction in the B field, and now my thumb is pointing towards you. Well, that's a direction along the wire. If this is a plastic tube filled with positive charges, and they're all being pushed towards you, and the wire goes that way, that's going to create a current. Now, I want you to look at this galvanometer here as I push this down between the poles of the magnet. Did you see it move? Okay, that's what lights up our city, okay? In Gilligan's Island, it was Gilligan, but in this case, it's me, okay? Now, many of us, I hope, when we were younger, made electromagnets. And what we did is we took some piece of iron like a nail, and then we wrapped wire around it, and then we hooked it to a battery to get that current going around and around in a loop. Gonna need your help again, okay? I've only got 2 hands, and someone needs to push down this button here. Okay, you see that what I've got here is just iron, it's not a magnet. But if I put this coil around it, go ahead. Okay. Suddenly it's a magnet. Okay, thank you. Now, Michael Faraday taught us that we don't need the battery. You don't need no stinking battery, okay? And I just want to pause here and mention that biographers describing Michael Faraday have not been terribly kind. One biographer described him as a man almost innocent. Now, ladies, I would ask you, does that look like a man almost innocent? No. Let me finish the quote. He was a man almost innocent of the principles of mathematics. In other words, they're saying he can't do math. This guy can't do math. And yet he's given us some of the most powerful physics of that the world has seen. And that's because he could visualize magnetic fields. He could look at this bar magnet and with his imagination see the field lines coming out of the north and spreading out and coming into the south. And with that incredible imagination, he was able to figure out how to light up our city. Now, let me just demonstrate for you what Michael Faraday demonstrated for the world. What he taught us was that if you take a magnet, watch that needle there. If you take a magnet and bring it towards a coil of wire, oh, that's a metal stand. Okay. We generate a current. See that current? Do that fast enough, you can generate a whole lot of current and light up your city. Now, I want you to notice something important, and that is if I bring that in here and park it, what did the needle do? Went back to zero. So it's not the presence of that magnetic field in there, it's the change, okay? When I bring it towards or bring it away, I get that current. We call that induced current, and by induced, I mean, I can't see the battery that causes it. It's like magic, okay? But it's not really magic, it's a magnetic force. Now, I'm gonna need some help here. If I bring that south pole close to a coil, Faraday teaches us that we get an induced current. Now, I hope everyone sees that whether I bring the magnet towards the coil or whether I bring the coil to the magnet, that's not really important, okay? So I'm going to bring the coil towards the magnet. And if I think about the magnetic field near this south pole, and that's what Michael Faraday could visualize, it comes in to the south pole. So if I drew the field lines that'd be curved here, but the magnetic field right here would be towards that south pole. Now, if I could get some help, would you help me, please? Okay, if you would stand right over there by the piano and hold this. This is the south pole. And let's make believe that this is a coil of wire, okay? Now, remember, we think of wire in our simplistic, cartoonish way as a plastic tube. Oh, look, it's a plastic tube filled with positive charge carriers. And when I push this towards the magnet, I'm taking all of those positive charges and giving them a velocity that way in a magnetic field that's towards the South Pole. So let's look at a little positive charge right at the top of this loop. What direction will the force be on that positive charge? Well, I reach in the direction of the motion. I turn my wrist so that I can wave towards that South Pole, and it's away from you. It's going to be pushed away from you. Well, now let's look at a positive charge down here. It's moving in a direction towards, what's your name?
Lizzie.
Lizzie? It's moving in a direction towards Lizzie in a magnetic field that's towards the South Pole. That's going to be pushed magnetically towards you. And so I would get something that way. Now, I can do this all day long. If I look at a charge right here, it's moving this way in a field that's towards the South Pole. That's going to be up. If I do it here, it's going to be down. All the way around, it's going to be pushed counterclockwise as viewed from me, clockwise as viewed from Lizzie. Thank you, thank you, thank you. Okay. Now, that's going to give me that induced current because I can't see the battery that's causing it. Now, does there have to be motion? Well, let's investigate that. And this is the second experiment that Faraday did. What he did is he took a second coil and he put it next to the first. And then he let me get this set up here. Put this over here. Let's call this new coil over here the primary coil. And I'm going to hook the primary coil up to this battery when the switch is closed. And right now the switch is open. This is a butterfly switch. It's only closed when I push down on the switch. But again, I would ask you to concentrate on the needle here, and you'll see that when I close the switch, that needle moves. Okay. Now, I was hoping that I would have a really sensitive galvanometer. We had one in Montana where you could see that move a lot. But here, it's just moving a little bit, but it is moving. And that tells me there's an induced current in there. When I put a current in the primary, it induces a current in the secondary. It's a secondary one that's connected to the ammeter. Galvanometer is just an ammeter. And it's a primary that's connected to the battery when I close the switch. So this is what it looks like, cartoonish. With the switch open, there's no current in either coil. When I close the switch, that causes battery current in the primary. And that is going to induce current in the secondary. But only for an instant. Only while I'm closing the switch, and then it goes away. And I can keep this switch closed all afternoon. I get nothing over here until I open the switch. When I open the switch, suddenly I get induced current the opposite direction of what I had when I closed the switch. And then that goes away. Okay. So again, it's not the magnetic field as it is the change in the magnetic field, is what Faraday decided. Now, that tells me that there doesn't have to be motion, but it does seem that there has to be a change in the strength of the magnetic field in that coil. And that's what Faraday thought for a while, until he had a brilliant idea for a thought experiment. Now, this thought experiment is one of the most famous in physics. And what you should imagine here is copper rails, really good conductor copper rails with a copper bar laying on top of them. And you're looking down from above like a seagull looking for a target, okay? Now, these two rails are hooked to the leads, to the terminals of this bulb. And that bulb is out, it's dark. Now, if we set up a magnetic field, that's what these little X's are, and that magnetic field is uniform. Tell your neighbor what that means, uniform. What's uniform about it? Okay. The fact that the field lines are evenly spaced tells me that I've got the same strength of B field here as I have here. Everywhere the magnetic field is the same strength. And I don't know how we're creating that magnetic field. That's not important. Somehow we set up a uniform magnetic field. Now, Faraday said, if I were to, with my hand, take this copper bar and slide it to the right. Again, a copper bar is like a copper wire. You can think of it as a tube filled with a bunch of positive charge carriers. Now, if I'm moving the bar to the right, I'm moving all of those charge carriers to the right in a magnetic field that's away from you. Okay, and so if I use right-hand rule number 1, the velocity of those charges is this way. In a magnetic field that's that way, my thumb is pointing up. And so as I move that, there will be a current that goes up. Now, we learned in the previous part of the class that I can't have a current in one part of a loop without having a current everywhere in the loop. What goes around comes around. And so that means I'm going to have current everywhere in this loop. And that's going to light up the bulb. Okay? Now, when Faraday thought of this experiment, he had a huge aha. He suddenly realized it wasn't the strength of the magnetic field that mattered. I mean, the strength of the magnetic field isn't changing here. What is changing in all 3 of our experiments is the number of field lines that goes through the loop. Let's look at this experiment. As we move the bar, we're making the loop bigger, and so I can get more of these field lines in there. When it was here, I just had 15. And when I get it over here, it's got more than 30. I changed the number of magnetic field lines. Now, if I go back to this experiment with the battery, when the switch is open, there's no field lines through this secondary coil. When I close the switch, the primary turns into an electromagnet, and that puts field lines through the secondary coil. Okay? And that induces the current. Now, if we go to the first experiment where we didn't have the battery, Michael Faraday, remember, he could visualize those field lines coming out of the north and spreading out. Okay? He could see them with his mind. And so he realized that when he was over here, those field lines spreading out, not many of them made it through that loop. They're going every which way. But when he got it closer and closer, more of those field lines got through the loop. I was changing the number of field lines through the loop in every one of those 3 experiments. See if your neighbor's on the bus. See if your neighbor's on the bus. Okay. So. In order to make physics as scary as possible for beginning students, we give this a name, magnetic flux, and a Greek symbol that just looks terrifying. But in truth, it's not hard. We have an induced EMF, and remember EMF stands for battery. An induced battery, invisible battery, can't see where it is caused by a change in the number of field lines through a loop. And that number of field lines is what we call magnetic flux. Magnetic flux. Okay? Now, it turns out that the formula for magnetic flux, the simplified formula, is just the magnetic field strength in Tesla and the area in meters squared. And a Tesla meter squared, we call a Weber, again, to honor a dead physics professor. Now, how do we get that formula, B times A? Well, let's see if I can motivate that. You remember how we use field lines. We said that the strength of the magnetic field was proportional to the number of field lines per cross-sectional area. Okay, if those field lines were closer together so that I had a lot of them in a unit area, then I had a strong magnetic field. Okay. Now, if I multiply both sides of that by area, I cancel out the area on this side, and we see that this product of the magnetic field strength in Tesla times the area in meters squared is going to be proportional to the number of field lines, the total number of field lines that go through the loop. So this would be the area of the loop, and this would be the field lines through the loop. See if your neighbor sees where we got that formula, please. Okay. Now, I'm a little disappointed here. I have always done this demo with flash bulbs. Now, how many of you know what flash bulbs are? Any? Okay. Back when I was alive, if you wanted to take a flash photograph, first of all, we didn't have cell phones, but the camera would have a little bulb on top. And this bulb you had to replace for every picture you took. Because when you push the button to take the picture, it hooked this, it connected this little bulb to a battery in the camera. And that caused a current that would take this magnesium filings that were in there and cause it to just explode. And it would give you a bright flash that would light up the room, and it would also destroy the bulb. And that was bright enough that you could see it in the back of the room. Well, we don't have any of those flash bulbs because they haven't been used in years and years and years. In Montana, we ran out. And so I started calling every camera shop in Montana looking for flash bulbs. And I happened to find one in a little dinky town. And the guy said, funny you should ask. I've just been throwing them in a couple of boxes in the back room. I've been saving them for years. I got 2 big boxes of them. And so I went and bought all of his flash bulbs. Montana State has enough flash bulbs to get them through the millennium. And I could have taken one of those boxes when I came down. But I've ordered some boxes. I found some on Amazon, but they won't come here for a week. And then I'll show you that demo, okay? Now, Oliver, I'm just gonna ask you to hold this up where people can see it, okay? Now, I want you to notice what happens when I bring this North Pole in through, this is a coil of wire. Look what happens when I bring it into the coil. Anything? No. And that's because I've been lying to you. What I told you was that this invisible battery depended on how much you changed the magnetic field lines through a loop. When in truth, what's important is how quickly you change. Is it flashing now? Okay. If I change the number of field lines quickly, I get a bigger battery, a battery big enough to make this flash. And indeed, if this were a flash bulb, you'd all be blinded right now. Okay. And that was always fun. You weren't really blinded. I mean, we tested it on grad students so that we knew that it wouldn't blind anyone. Okay. Now, this is Faraday's law. This is almost Faraday's law. It is oh so close to Faraday's law. There are just a couple of things missing. But the important part of Faraday's law is that it's not only how much you change the number of field lines, that's the upstairs part of this equation, but it also depends on how quickly you change it, okay? Remember, whenever you have a definition that is a ratio, something divided by something else, set the basement equal to 1, in this case, 1 second. So it's how much the field lines change in a unit of time, how quickly you change them. Now, the left-hand side is this invisible battery that drives the invisible current, the induced current. And there's a minus sign in this equation that is one of the most famous minus signs in all of physics, indeed all of science. It even has its own name. It's called Lenz's law. And that is the topic of next week's tutorial and Tuesday's lecture. And Tuesday's lecture is, in my mind, the funnest lecture in 106. On Tuesday, we're going to do the quantum levitation track. We're going to do all sorts of fun demos next Tuesday. In my mind, Newton's third law is the most elegant, most beautiful physical law, and Lenz's law is a close second. So we'll have fun with that on Tuesday. Now, there's one more piece that's missing, and that is that when I bring the magnet close to this coil with only a few turns of the coil, I don't get a very big current, do I? It doesn't move very far. But if I take this coil that has a lot of turns and I hook it to the ammeter, watch what happens now. I get something big, right? Indeed, if I'm not careful, I could break that needle, okay? So it turns out that the number of field lines through the loop depends on how many wires, how many loops there are in that wire, in that loop. If I had a region with magnetic field lines, let me get a different color for that. If I had one loop that's enclosing 9 field lines. But if I have 2 loops, it's enclosing 18, 27, 36. You see how this is going? And so for every loop of the wire, I have to count those field lines again. One way to think of that is that, let's say I had a smaller loop. Instead of putting them on top of each other, I could say, oh, you know, there's 2 there and there's 2 there. Each one of the loops is enclosing field lines. Now, what that does to our equation is that we have to modify how we define magnetic flux. The real formula for magnetic flux is not B times A, it's National Basketball Association. Okay, can you remember that now? National Basketball Association. The N is the number of loops in the coil. Okay. Now, what can we do with this? Well, suppose you were in charge of guarding the border and making sure that it was safe. And you know which border I'm talking about. We're talking about the border with Canada, our arch enemies that we have always been at war with. Okay? And so you're guarding that border up there, trying to keep all of those crafty Canadians from sneaking across the border with magnets. And so what you could do is you could take a door frame that you got at Lowe's and you could wrap wire around it and hook it to an ammeter, a galvanometer, by any other name. And then if those Canadians tried to go through the door with a magnet, you got them. Okay? You nailed them. You send them right back to Canada. Okay, where they'll have free health care.
So if you walk through really slow, will it not set it off?
Hold that thought. Hold that thought. What if instead you were trying to protect Canada from Americans? And Americans are a violent crew, okay? We're not trying to get magnets through that barrier. We're trying to bring guns, and this is the closest thing to a gun that I was able to get. Well, you see that it's just a chunk of iron, and it's not doing anything there. So the question is, how could I, instead of making a magnet detector, make a gun detector, a metal detector? Well, one way is to, put a greeter there at the border that would say, excuse me, sir, madam, could I please see your gun? And then you could put a real magnet onto it. And then when it went through, it would move the needle, okay? Now, let me see if this would be more effective here. Okay. Now, that doesn't seem very effective. That's just going to catch the not so smart criminals that are trying to bring a gun across the border. But the other way we could do it is we could take a second coil around that door frame, and we could hook that one up to a battery. And then when the gun went through this first coil hooked to the battery, it would get magnetized, like our electromagnet. And then when it went through the second coil, it would trip the alarm. Okay, so again, close the switch. Okay, so close it. Okay. Oh, open it. Am I connected? No, I'm not connected. Someone should have said something. Old people can be so slow. Well, that didn't change things very much. Let's try this one. Okay, close it. There we go. I got him. I got him. Okay, thank you. Now, again, with a more sensitive galvanometer, you would see that swinging all over the place. Hopefully I'll have one of those by the 12 o'clock class. How could you sneak that gun through this metal detector? You want to answer that, good sir?
Walk slow.
Oh, yeah, yeah. What we found is that time matters, how quickly you change the number of field lines. So essentially, you get through that like this. It's the old ladies that are packing. Yeah. Okay. So you're gonna have to have some bouncer at the door throwing these people through the door so that it will trip the alarm. Now, folks, before you go down to the airport and try getting through that machine, this thing works on direct current, and I can go slowly and fool it. Their machine's very sophisticated and runs on alternating current, and if you try this, you're gonna get a free colonoscopy, okay? So don't be doing this. Don't be doing it. Okay. I have here a problem of Faraday's law problem that's very similar to one of your homework problems. Okay. We have a wire and it's looped 10 times around a square. The square is made of some insulator. It's just holding the wire in place. And it's 2 centimeters on a side. If we start up a magnetic field into the page and the diagram at right, so that it increases at a rate of 10 to the minus 5 Tesla, a tenth of a Gauss, each second, what EMF, what magical invisible battery will be induced between the ends of the wire loop, the 2 little pieces that are hanging down there? Well, let's solve that together. I know that the induced EMF is given by Faraday's law, which is minus the change in flux, magnetic flux, divided by the change in time. Now that minus sign we call Lenz's law, and we're not there yet. So we're just going to look for the magnitude of the EMF. And so I want the magnitude of that. And so that's just going to be the change in flux divided by the change in time. Now, remember that flux is equal to National Basketball Association. And so if I want the change in flux, that's going to be the change in National Basketball Association. Well, we're not changing the number of loops, and we're not changing the area of the loop, but what we are changing is the magnetic field. Okay? So I can write this up here as the number of turns. Oh, I didn't spell A right. Do you have days where you can't even spell A? You Canadians, how do you spell A? E-H? Okay? I've been really rough on the Canadians today. I love Canada. I really do. Okay. So this is going to be N times A that I spelled correctly this time, times the change in B divided by the change in time. Now, that change in B with respect to time is the rate at which we're changing the magnetic field. That's the 10 to the minus fifth Tesla per second. And so if I plug that 10 to the minus fifth Tesla per second, and this is my area. Remember, I've got to put things in standard units. For distances, that would be meters, and 2 centimeters would be 0.02 meters. And then I square that to get the area. Okay. And what I get, if you work out all of these units, a Tesla meter squared, that's a Weber per second is a volt. And so what we get is 4 times 10 to the minus 8 volts. Now you have a problem that's almost identical to that, but the value of N is 1 in that problem. See if your neighbor's on the bus, please. Do a buddy check here. Question back here. How can I help? No, the area is going to be length times width. And the length is 0.02 meters and the width is 0.02 meters. Yeah, okay. Okay. Let's go back to this thought experiment of Faraday's and think about some implications here. If I could make this set of rails really, really long, they just go on forever. And remember, we're looking down on this, and the copper bar is resting on top of those rails. If I could get rid of the friction between the rail and the bar, it seems like I wouldn't need the hand. Well, I'd need the hand to get the bar going, but we learned in physics 105 that once something gets going, it just wants to keep going. And so that thing would just slide along the bars for miles, and it would just continuously make electric current. Free energy. I don't even have to push. Well, I have to push to get it going, but then I go home. Well, that doesn't feel right to us, I hope. I hope that feels like a free lunch and your parents warned you against that, okay? So let's look at why that doesn't work. Well, if I push that to the right, that bar, I'm pushing, remember, I think of that bar as a plastic tube with charge carriers. I'm imposing a velocity this way. And that's what gave me the current to begin with. But once that current starts, that's another velocity. I've got one velocity due to the bar going that way, but I got another velocity due to the current going this way. Now, the velocity this way is what gave me the push up, but the velocity this way gives me a magnetic push back that's fighting the motion. And so I don't get free lunch. I'm going to constantly have to push. I'm going to have to constantly be doing Verk to get that current. That current has to be paid for by physical work, or as we call it, Verk, physics work. Okay? See if your neighbor understands that principle, please. Do a buddy check there. Okay. Now it's this simple idea that is really just conservation of energy that lights up our cities with generators. Okay. Now a generator is very, very simple, very, very simple. I just have a magnetic field caused by who knows what, horseshoe magnet, 2 bar magnets, electromagnet, it doesn't matter. But if I turn a coil of wire in that magnetic field, I'm changing the number of field lines through that coil. Think of this coil as a butterfly net. We've got a bunch of butterflies in here. If I swing like that, I'm catching butterflies, right? If I swing like that, I'm just making them mad, okay? I'm just smacking them, okay? I'm not catching any of them. And so if I think of these as butterflies, I'm catching butterflies, I'm not. I'm catching butterflies, I'm not. I'm catching butterflies, I'm not. I'm continually changing the number of field lines through the loop. Now, that's what a generator is. Now, the simplest generator would turn that coil with a human, either me or Gilligan. And so here I've just got the coils that are inside this is just a drill from, I think, Home Depot. And if I turn that, I am generating an induced battery, an EMF. But I'm not generating any current right now because there's not a complete loop until I close the switch. Okay. Sir, you look strong. Come on up here. Okay. If you could turn that switch, turn that crank to keep the bulbs lit. I'm gonna light up more and more bulbs. Okay. What happened? It got harder. It got harder. Thank you. Let's give him a hand, folks. The reason it got harder is because as we added more and more bulbs in parallel, we were asking for more and more current to go through that circuit. which went through the coil that was being turned in the magnetic field. Now, if we think of that current that's generated, it's always going to be in the direction, always, 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 such that we have to fight the motion. Okay, it will fight the motion. It's always going to be in a direction to make things harder for us to turn, because it got harder the more current we have. And so if I am turning this way, well, you know that the magnetic dipole wants to line up with the magnetic field it finds itself in. If I have to turn it the other way, I have to fight. It doesn't want to go that way. And so as I turn, it's hard. And the more current I've got going around that loop, the bigger the little bar magnet I'm trying to turn in the way it doesn't want to go. And so it will fight me even more. Now, as I move that around here, now, if I keep on turning, the little bar magnet is going to help me. But that's not the way the world works. The world is going to make that current go so that it always makes it hard for us. We always have to do positive air. And so watch those current, the X on the top and the dot on the bottom. 1, 2, 3, pow. Okay, and then suddenly they go the other way, so that you're always fighting. And then pow, and then they go the other way, so that you're always fighting. Okay? See if your neighbor understands a generator. Okay. In practice, we don't have a strong person at some crank somewhere. What we have are turbines at the bottom of a dam. And as water falls over the dam, it causes these turbines to go round and round, and they're connected to these coils of wire. And these coils of wire are forced by the falling water to turn in a magnetic field, like what we saw up there. Now, we talked about a brownout the other day. If everyone in Los Angeles turns on their air conditioner at the same time, well, that's adding a whole lot of paths in parallel. That lowers the resistance of the city of Los Angeles. That demands a huge amount of current. The more current that's running through these coils at the bottom of the dam, the harder it is for the coil to be turned. It fights harder. And when it gets so much current in there that the falling water can't make the coils go around, we black out the city of Los Angeles. Okay, now we're gonna see if we can do that. Good sir, if you'd come back. Instead of hooking this to a circuit, I'm just gonna hook it to a wire. And that's gonna essentially make the resistance in the circuit negligible, almost nothing. See if you can turn that like you did before. So harder or less? Harder, okay. Thank him again, he's doing a lot of work here. Okay. Now, big question, get out your clicker. I've got an electric fan there. Is that a motor or a generator? Motor, generator, both, neither, or I don't know. Let me get you started. Okay, now you can click.
But then.
Good thing we don't have to write.
Okay, get your vote in. Okay, it turns out that the answer is C. Both. It turns out that anytime you have a motor, you're turning a coil of wire in a magnetic field. Now, I could turn that coil of wire in the magnetic field with the crank, okay, and then it would be a generator. But instead, I was using the power supply, could have been a battery, to make that go round. However that coil goes around in the magnetic field, I'm changing the number of field lines through the coil. That's going to induce current. Now, the difference is the battery current is causing the coil to turn. The induced current is fighting that turn. And so they're going to be pushing against each other. We call that a back EMF, and we'll talk more about that next day on Tuesday. But that's going to open up a can of worms that we don't have time to deal with today. So let's start our weekend early, shall we? Okay. Yeah, let's go. Thank you.